All right, in this lecture we're going to talk about approximation error. Approximation error is the absolute value between the difference of the actual area under a curve between two endpoints, x equal a and x equal b, and the right or left sum. In our last lecture we calculated the left and right sum with 16 rectangles whose bases formed 16 equal line segments between 1 and 5. The actual area under the curve is 14 1/3 square units. But the left sum gave us 13.59 and the right sum gave us 15.09. So we can calculate the error. The error for the left rectangles is the absolute value of the difference between the true area under the curve and the left rectangle sum, and gives us an error of about 0.7433. We are rounding it off. The error for the right rectangles came to 0.7567. Again, we're rounding off. When we look at the picture, we notice that the error can be bounded by the area in the empty or clear rectangles. Notice that they all stack up on top of each other. This only really happens if the function is always increasing from left to right, from a to b, or always decreasing from a to b. Let's see if we can calculate the area of the sums of those rectangles. Now, since they stack up like boxes, all we need to know is the total height and the width of one of the rectangles. So we calculate the error bound, or an upper bound for the error, by computing the height, which is f of 5 minus f of 1 absolute value. We need absolute value because, remember, if it's decreasing, then f of 5 will be less than f of 1. In this picture, it's increasing, so f of 5 is bigger than f of 1. And then we multiply by the base. Remember, the base is delta x, or a small difference between the successive values of x. And we get 7.25 minus 1.25 times 1/4, or 1.5, which is indeed bigger than the error we got when we calculated them exactly. And this gives us our theorem. An error bound for approximations of area by left or right sums, where f of x is greater than 0, meaning that we're going to compute the area between the curve from a to b and the x-axis, and when the function is either always increasing from a to b or always decreasing from a to b, then the error bound can be given by the absolute value of the difference between f of b and f of a, and that will be the height of the clear rectangles, times the base. And remember that that delta x, that base, is given by b minus a over n, where we take the distance from a to b and divide by n. All right, let's do some calculations of our own. This time, let's calculate the left and right sum for 6 rectangles to approximate the area under the curve of the function f of x equal 9 minus x squared over 4 from x equal 2 to x equal 5. We will also calculate the error bound. All right, so if we want to divide the interval from 2 to 5 into 6 equal rectangles, 6 equal intervals on the x-axis, then our base is going to have the size 5 minus 2 over 6, because we want 6 of them. That's 3/6, and that gives us a delta x, or base, of 1/2. Okay, so let's calculate the left sum. We're going to take 6 equally spaced values on the left-hand side of these rectangles, and L6 will be f of 2 times 1/2 plus f of 2.5, right, 1/2 times 1/2. Each of these will progress by 1/2, plus f of 3 times 1/2, we're halfway there, plus f of 3.5 times 1/2, plus f of 4 times 1/2, and finally plus f of 4.5 times 1/2. We just have to calculate the values of the function 9 minus x squared over 4 at each of these numbers. What did we come up with? F of 2.5 is 119/16. F of 3 is 27/4. F of 3.5 is 95/16. f of 4 is 5, and f of 4.5 is 63/16. If we convert them all to 30 seconds and add them up, we get 593 30 seconds, or 18.53125. Now let's calculate the right sum. We'll scroll down a little bit. And in the right sum, we'll add up 6, but we'll start at 2.5 and go from 2.5 to 5. So we calculated the height of each rectangle at the right point: 2.5, 3, 3.5, 4, 4.5, and 5. We multiplied by the base, 1/2. We converted them all to 30 seconds so that we could add them up, and we got 509 30 seconds, or 15.90625. And last in this set, we want to calculate the error bound. We'll calculate the error bound using our theorem. So the error, in other words, the error for L6 and R6 will be less than or equal to the following value: the absolute value of f of b minus f of a times delta x b minus a divided by 6 rectangles. Well, let's see. F of 5 turned out to be 11/4. Minus f of 2. F of 2 turned out to be 8 times 1/2. That comes out to be, let's see, 8 is 32/4 minus 11/4 times 1/2. Or we get 21/4 eighths. If we multiply the 4 times the 2, and we divide, we get 2 and 5/8, 625. And we've calculated the error bound. The next question that we want to answer is a little more complicated. For part B, or part 2, how large should n be in order for the approximation by either the left or right rectangles to be within 0.05 of the true value? In other words, we're going to calculate our error. So part 2, we're going to calculate our error without deciding yet what n is. We can do this easily because the f of 5, f of b minus f of 2, that part doesn't change. And the 5 minus 2 doesn't change, b minus a, but we don't know what n is. We just know that we want this to be less than or equal to 0.05. To make this kind of calculation, we need to do some simplifications, right? Well, we've calculated our 11/4 minus 8 before and got 21/4. So we'll get 21/4 times 3 over n, and we'll want this to be less than or equal to 0.05. And remember that n is going to be greater than or equal to 0. So if we multiply both sides by n, then we will not change the direction of our inequality. Okay? If we multiply the 21 times 3, we get 63/4 times 1 over n is less than or equal to 0.05. Now I'm going to multiply both sides by n, and I'm going to get 15.75 is less than or equal to 0.05 n. This might be a good time to remember that 5 1/100ths is 1/20th. So I multiply both sides by 20, and we'll get 315 is less than or equal to n. So I would have to divide up the interval from 2 to 5 into at least 315 equal line segments and get 315 rectangles in order for my approximation error to be less than or equal to 0.05 square units. And now I'd like for you to try a similar problem on your own. Given the function f of x equal 8 minus x squared over 2, how large should n be in order for the approximation of the area L sub n or R sub n to be within 0.5 or 1/2 of the true value? Here are your choices. You need to get out your pencil and paper. If you haven't done that, I'll go back. Make sure that you write down the equation and the equation for the error bound. Leave n unknown. You want your error to be less than or equal to 0.5. And you need an n that's at least greater than or equal to one of the 4 following numbers. Or none of these if you get a better estimate. Thank you.